Let's move on to the plenary section. I invite Mrs. Shani Agustin, faculty member of the Department of Chemistry, to introduce our plenary speaker, Dr. Gurpreet Kaur.
Good morning to one and all. In June 1999, Richard Smalley, Nobel laureate in chemistry, addressed the US House Committee on Science on the benefits of nanotechnology, the impact of nanotechnology on the health and lives of people. He said, will be at least the equivalent of combined influences of aided engineering and man-made polymers developed in this century. On the auspicious occasion of our webinar, we have an eminent Dr. Gurpreet Kaur. She is working as Assistant Professor of Chemistry in Government College for Women, Parade Ground, Jammu and Kashmir. She completed her MPhil and PhD in inorganic chemistry from University of Jammu. She has numerous publications and she presented papers in various conferences. We are grateful for your presence and a warm welcome to you, ma'am. We are excited to hear from you, ma'am. Thank you.
Thank you, Sharni ma'am. Am I audible?
Yes, ma'am.
First of all, I would like to thank Dr. Leena Matthew, the Principal BK College for Women, Amalgiri, Kerala, respected Dr. Saif Ali Chaudhary, Professor Department of Chemistry, Jamia Millia Islamia, New Delhi, Dr. R.S. Regin, Co-Patent Cope Comorin Trust, for inviting me over here, Dr. Sister Ali Joseph, for giving me the opportunity to speak on the occasion, other dignitaries, scholars, students. So very good morning to all. First of all, let me share the screen and kindly let me know if it is available. Actually, I have not taken the very technical things of the nanotechnology, nanomaterials in concern, because I was thinking that most of the students will be attending the program, and I have tried to kept it very conceptual and very basic. So the topic of my presentation is nanomaterials and introduction. Ma'am, am I audible?
Yes, ma'am.
Is the screen clear?
Yes, ma'am.
So the topic is nanomaterials and introduction. The concept of nanotechnology deals with the study of manipulating any material at atomic level, or more precisely at the nanoscale, producing nanomaterials. 1 nanometer, all of you must be knowing, is a unit of length in metric system and is equal to 1/1,000,000th of a meter. It is approximately the width of 3 or 4 atoms, or we can say the about 1 upon 25,000 times the width of human hair. Nanomaterials are one of the main products of nanotechnology, as nanoparticles, nanotubes, and nanorods. The concept was proposed by Dr. Richard Feynman in 1959, an eminent physicist who earned Nobel for this. Nanoparticles can display properties significantly different from the bulk material, because at this level, quantum effects may be significant and may appear to be very prominent. Simply, we can say the mechanical, electrical, optical, electronic, catalytic, and magnetic properties of the solids are significantly altered with great reduction in the particle size. Now let me clear it. What's the difference between nanomaterials and bulk material? There are two principal factors that cause the properties of the nanomaterials to differ significantly from other materials. The first one is their increased relative surface area, and the second one is the quantum effects that come into force only in the nanoscale, or in the very small scale. These factors can change or enhance properties such as reactivity, strength, and electrical characteristics of any substance. As a particle decreases in size, a greater proportion of atoms are found at the surface compared to those inside. For example, if we take a particle of 30 nanometers, say, it has 5% of its atom exposed at the surface. But when the same particle is taken at 10 nanometer scale, 20% of its atoms are exposed. And if we take it at 3 nanometer, 50% of the atoms are exposed. Thus, nanoparticles have a very much greater surface area per unit mass compared with the large particles. As growth and catalytic chemical reactions occur at surfaces, this means that a given mass of material in nanoparticulate form will be much more reactive than the same mass of material when taken with the larger particles. We can take an analogy to understand the concept of nanomaterials. Let us take a silver coin having 30 grams of silver in it with a total surface area of 3000 square millimeter. If the same amount of coin silver were divided into tiny particles, say 10 nanometer in diameter, it means we are dividing this 30 gram of silver coin into 10 nanometer in diameter particles. The total surface area of those particles would be 7000 square meters, which is equal to the size of a soccer field, that is about 5100 square meters. In other words, when the amount of coin silver contained in a silver coin is rendered into 10 nanometer particles, the surface area of those particles is over 2 million times greater than the surface area of the silver coin. Two important inventions led to the development of nanotechnology and the subsequent development of the nanomaterials. The first one is atomic force microscope. The microscope available to us before this was not able to penetrate the surface enough to determine the topography of the atoms on the surface. This atomic force microscope, which was used for measuring the atomic topography of the surface by means of repulsive force between the surface and the tip of the microscope probe moving above the surface. And the second invention is your scanning tunnel microscope. It is a device that obtains images of the atoms on the surface of the material. STM is not an optical microscope, rather it works by detecting the electrical forces with a probe that tapers down to a point only a single atomic cross. That means you can find out the morphology, the topography, and the other sizes related to the atom at the very first stage. So let us see how the classification of nanomaterials is being done. Nanomaterials can be classified in different ways, and one of these ways is taking the dimensions of nanomaterials into concern. First of all, we'll be taking zero-dimension nanomaterials. Zero-dimension nanomaterial means all the dimensions x, y, and z of any material are at the nanoscale. That means no dimensions are greater than 100 nanometer. All the dimensions, whether in the x-axis, y-axis, or z-axis, they are having a dimensions lesser than 100 nanometer. For example, we are having nanospheres, we are having nanoclusters. Although we have nanoclusters belonging to one-dimensional nanomaterials also. Then one-dimensional nanomaterial means two dimensions are the nanoscale and the other one is outside the nanoscales. This leads to formation of needle-shaped nanomaterials. That means two dimensions, dimension maybe x, y, they are lesser than 100 nanometer and the rest is more than 100 nanometer. The category included in this nanofibers, nanotubes, nanorods, and nanowires. Then we have two-dimensional nanomaterials. Excuse me. Here, one dimension is at nanoscale and the other two dimensions of the matter are outside the nanoscale. They have a plate-like structure, for example, nanofilms, nanolayers, and nanocoatings with nanometer thickness. Three-dimensional nanomaterials, these are not confined to the nanoscale in any dimension. They have arbitrary dimensions above 100 nanometer, and they are composed of multiple arrangement of nano-sized crystals in different orientations. It includes dispersion of nanoparticles, bundles of wires, nanowires, bundles of nanotubes in which zero-dimensional, one-dimensional, and two-dimensional structural elements are in close contact, forming the three-dimensional nanomaterials. These are the structures representing zero-dimensional, that includes fullerene, one-dimensional nanomaterial, that is carbon nanotube. Two-dimensional, when we separate the carbon nanotube, we'll be getting two-dimensional graphene having x-axis and y-axis in nanoscale. And then we have three-dimensional, that is graphite. When the sheets of graphene are stacked over one another, we'll be getting three-dimensional graphite. Here is a graphene, which is the most researched, most popular, and most recent nanomaterial being done in the research. I have also done my work on graphene, but I have not taken it here just for the basic conceptual things. So this is your 2D graphene nanomaterial, two-dimensional nanomaterial. That includes graphene. That includes boron nitride. This is a nanosheet of boron nitride with blue color balls representing boron, and the pink color balls representing this nitrogen. Then we have tungsten diselenite with tungsten in blue color and selenium in yellow color. All these are two-dimensional nanomaterials having nanoscale dimensions in X and Y directions. In recent years, two-dimensional nanomaterials such as graphene, hexagonal boron trinitride, they have attracted a lot of attention due to their satisfactory properties and widespread uses in the electronics, optoelectronics, catalyst, energy storage facilities, sensors, solar cells, lithium batteries, and composites. It is the most famous two-dimensional nanosheet, graphene, that is composed of carbon atoms in a hexagonal honeycomb configuration with sp2 hybridized atoms. It is also the most important member of the multi-dimensional carbon material family that is formed by putting together carbon atoms, and which included fullerenes as a zero-dimensional material, carbon nanotubes as one-dimensional, and graphite as a three-dimensional nanomaterial. This is how zero-dimensional converts into two-dimensional and three-dimensional. Single-layer graphene is a substructure. This graphene is a substructure for the construction of carbon structures, which if we placed on each other, they produce three-dimensional graphite. And when we roll up it in this form, we'll be getting nanotubes. And when we roll up like a socket ball, we'll be getting fullerenes. So same sheet can be converted into zero-dimensional, two-dimensional, and three-dimensional depending upon their placement over the space. As far as single-layer graphene is confirmed, it is a two-dimensional nanosheet arranged in hexagonal network, and sp2 hybridized carbon is bonded to three another atoms with a strong covalent bond and that are configured in a hexagonal structure, and also has a pi orbital perpendicular to the sheet that form pi bond out of the plane. Graphene is considered as a semi-metal or a semiconductor with a band gap of almost zero. It means it has a very high electron mobility even at room temperature. It is the hardest and thinnest substance ever produced by mankind, despite the fact that it has a dense structure due to its very thin thickness, which is equal to almost thickness of a carbon single atom. It allows light to penetrate through it and is highly transparent. It is also very conductive, even more conductive than the copper, 200 to 300 times stronger than steel and even harder than diamond. However, it is very light and flexible. In addition, one of the properties of graphene is the great ability to move charge carriers. Electrons have relatively freely throughout graphene. Now, what are the recent applications of graphene? As reinforcement in composites, instead of carbon fiber, this results in the creation of lighter and stronger aerocrafts and satellites. They are used instead of semiconductor silicones in transistors due to superb conductivity. So this is a very promising material for the replacement of silicons in semiconductors. Then embedding graphene in plastics enable them to conduct electricity in some cases. It also increases the durability of batteries using in the dust form. It makes harder, stronger, and lighter plastics as conductive, transparent coating for solar cells and screens. For producing stronger implants, which is the major research area now being done, nowadays being done for the medical implantments of the artificial medical stunts. Creating supercapacitors and the applications in the liquid crystal display. They have application in flexible touch screens and displays that we find nowadays. We find the flexible mobiles turning their screens upside down, and in the light emitting diodes. So this was about graphene, that is a two-dimensional versatile material. Then we have one-dimensional nanomaterials. These materials have a dimension again within the range of 1-200 nanometer, but in a single dimension. The morphology, composition, structure cover a large variety, including wires, rods, tubes, ribbons of metals and semi-metals, oxides, sulfides, and halides. So the most important one-dimensional nanomaterials in use are nanotubes, nano rods, nanowires, nano clusters, and the most recently nanocones. So what are these nanotubes? When we this twist the graphene sheet into one dimension, we'll be getting carbon nanotube. That is, just rolling up graphene sheet, you will be getting carbon nanotube. These are long hollow structures, walls made up of one atom thick sheet of carbon, having higher strength to weight ratio and can be used in creating lightweight aircrafts. They can easily penetrate membranes and thus help in cancer therapy. That is the most prominent application of nanotubes nowadays. The carbon nanotubes, they were identified in 1991, but the recent research proves that they have a tremendous applications in biomedical sciences. They have tube-shaped material made up of carbon having a diameter less than 1 nanometer even. Simply, we can say these are cylinders of one or more layer of graphene. These show a unique combination of stiffness, strength, tenacity compared to other fiber materials. Thermal and electrical conductivity are also very high as compared to the conducting materials. So what are the application of carbon nanotubes? Carbon nanotubes have the intrinsic characteristic desired in material used as electrodes in batteries and capacitors. Two technologies of rapidly increasing importance. They have a tremendously higher surface area, good electrical conductivity, and very importantly, their linear geometry makes their surface highly accessible. These have the highest reversible capacity of any carbon material for being used in lithium ion battery. In addition, they are outstanding material for supercapacitor electrodes and are now being marketed for this application. Nanotubes have application in a variety of fuel cell components. They have a number of properties including higher surface area, thermal conductivity, which make them useful as electrode catalyst support in PM fuel cells. They may also be used in gas diffusion layers as well as current collectors because of their very high electrical conductivity. Then they are being used in drug delivery. Carbon nanotubes are promising the drug delivery platforms that can be functionalized with a variety of biomolecules such as antibodies, proteins, or DNA for target delivery of the drugs. They can easily penetrate cells, having a very small thickness, delivering drugs directly to the cytoplasm or the nucleus, making the medical treatment more efficient and more rapid. Then they are being used in cosmetics. A large number of nanosystems or novel nano carriers are commonly used in cosmetic formulations to encapsulate active ingredients for their efficient delivery through the skin barriers. These nanosystems can help absorption or penetration of cosmeceuticals active moieties within the epidermal layers in a remarkable way of achieving burst or sustained release of actives. Parallel carbon nanotubes have been used to create loudspeakers. They can serve as a multifunctional coating material and they can be used to produce further nanowires. Then we have one-dimensional nanorods. These are nanostructures that are the object of fundamental and applied research nowadays. May be prepared from carbon, may be prepared from gold, zinc, and many other materials. They are bigger than individual atoms and also smaller than the small molecules. These have typical length of 10 to 120 nanometer. For example, metallic nanorods, semiconductor nanorods, carbon nanorods, and oxide nanorods. They are essential for the development of electronic, optical, magnetic, and micromechanical devices. Among these one-dimensional structures, they have an advantage as it can be made from most elements, most of the metals and non-metals and compounds. And for the synthetic requirements of their production are more flexible than the nanotubes and nanowires. Nanorods made up of carbon are also known as carbon nanorods or diamond nanorods. These have a crystalline structure like diamond with the sp3 hybridization. What are the recent application of nanorods? They have been used in display technology because the reflectivity of rod can be changed just by changing their orientation with an applied electric field. They are being used in cancer therapies. They are used in transistors, solar cells, diode lasers, LEDs, and they may increase the efficiency of silicon voltaic cell. They are also significant for optical applications like biological sensors. They are also used as photocatalyst. They have potential application in spectroscopy and fluorescent medical imaging. Then we have another one-dimensional nanomaterial that is nano clusters. It is a grouping of number of nanoparticles in a narrow size distribution, having at least one dimension between 1 to 10 nanometers. Simply, they are just a fine aggregates of atoms or molecules in making a structure. They contain a couple of hundred atoms, but the larger aggregates may have more than 1,000 atoms. That is known as nanoparticles. The number of atoms in the cluster of critical size and higher stability is called the magic number. Nanoclusters are bridge between bulk material and atomic or molecular structures. It's used in biotechnology and pharmacology. It has potential application in microelectronics, telecommunication, sensors, transducers, electroluminescent displays, and catalysis. Then we have nanowires. You can see the dimension, the distance between two, so many nanowires can fit into 2 micron meter distance. These are the structures which have a diameter of the order of nanometer and unconstrained length. That means they are much longer than their diameters. They are also called quantum wires because at this scale they have a different quantum mechanical effects. There are different type of nanowires. For example, we have molecular wires, we have metallic nanowires, we have carbon nanowires. They are used in digital computing. They are used for the preparation of active electronic components like PN junction, like logic gates. They have potential application in high density data storage. For example, silver chloride nanowires are used as photocatalyst to decompose organic molecules in polluted water. Now, the recent advances in nanowires, researchers at the University of Massachusetts have developed protein nanowires that produce electric current when exposed to water vapor in air. Researchers at MIT have developed a solar cell using graphene coated with zinc oxide nanowires. They believe that this method will allow the production of low-cost, flexible solar cell at high enough efficiency to be competitive. Researchers at Nagoya University, they are developing a nanowire-based sensor to detect indicators of bladder and prostate cancers in the urine sample. Then we have nanocones, the recent ones. They are conical structures made from the carbon, having at least one dimension of the order of the micrometer. They are obtained from wrapped graphene sheets. They are different from nanowires and as these have height and base diameter of the same order of the magnitude. From electron microscopy, it is clear that the opening angle, that is the apex of the cone, is not arbitrary, but it has a preferred values of approximately 20, 40 or 60 degree. They have interesting applications in nanolithography. They are used in chemical sensors, biosensors, spectroscopy, etc. They are used as electrode material in lithium-ion batteries. What are the recent advances in nanocones? Organic chemist Frank Wirchner and postdoc fellow Kachua Shoma of University of Würzburg came up with the method of synthesizing the nanocones, which are about 1.6 nanometer in diameter and 0.432 nanometer tall. A 5-atom ring of carbon forms the cone's tip. The team used a cross-coupling annulation cascade to add hexagons around the edges of the ring until the molecule grew to 80 carbons. The team added 5 nitrogen atoms also around the periphery, increasing the crystal solubility. These cones could prove more soluble in organic solvent than graphene. Their solubility is necessary for making the thin films to build devices such as solar cell components out of the material. The nanocones also absorb light across most of the visible spectrum better than the fullerenes. Like fullerenes, they were also electron poor. Those two properties make them useful for creating efficient organic solar cells. And the nanocones fluorescence could make them useful in sensor application. The overall yield of the full-size cone was, however, just 0.6% because the strain induced by the molecule's cone tap. So we have some restriction over it that the yield of the cone is very low. Now, what are the recent advances that are soon to be reality in nanotechnology? Nanotech meets contact lenses, virtual reality. The research is going on, all the points mentioned over here in different universities of the world, and they are soon to be reality in nanoworlds. A nanotech detector for heart attack that is attached to your beneath your heart. Then tiny 3D printing batteries, revolutionizing eye surgery, creating biodegradable electrodes, and nanotech enable breathalyzers for diabetes. And at the end, I would like to say nanomaterials and nature, how are they correlated? Nanomaterials can be found everywhere in nature and have been the part of environment since our planet was created about 4.5 billion years ago. Fullerenes or graphenes, which are of nano size, have even been found in space while they have been synthesized by man only recently. Wood is one of the most common natural nanomaterials. It has a hierarchical scale structure. At the largest scale, it contains soft fibers with a diameter of about 20 to 30 micrometer and a length typically of 2 to 5 millimeter. At an intermediate hierarchical scale, nanofibers are present with a diameter less than 100 nanometer and a length greater than 1 micrometer. The smallest scale contains crystallites with a width less than 5 nanometer and a length less than 300 nanometer. Nanocellulosic materials are also found in nature. They can be collagen fibrils originating from animal sources, nanofibers originating from wood, plants, crops, or bacteria. Crystals are whiskers deriving from wood, plants, and crops. Nature has developed several ways to build macroscopic systems from the nanobricks, like the seashell or bones. Thank you very much.